Okay, so let us do the second part. So from trigonometric ones, you need to know one more. Of course, I have written it in terms of secant. In principle, you don't need to know about secant, but they might give you in the exam like 1 over cosine kx squared or 1 plus tangent kx. So I want to describe these two formulas as well here for you on the board. So, of course, the next natural step is not talking about, 1 over cosine x squared. What is the most natural one step to start with? After learning about the integral of sine and cosine, usually you think about integral of tangent. Okay, but the integral of tangent, we will learn how to do it, but it will come later. Okay, but the one that we can do now is actually integral of secant. If you're not comfortable with secant, I will change it. So secant of an angle is nothing except 1 over cosine of that angle, and cosecant of the angle is 1 over sine theta. That's it. It's not something very mysterious.
What about tangent?
The tangent is sine over cosine.
The reverse of tangent.
The reverse of tangent is also called cotangent. It's 1 over tangent. Well, okay, so if you want to do this, this can be viewed as, there is a formula we talked about that before when we were differentiating. So this means 1 over cosine kx to power 2 dx. Now, do you remember anything in your memory about a function whose derivative is 1 over cosine squared? We had this before, that's just tangent. So if you remember, we talked about the derivative of tangent of x. It becomes 1 over cosine x squared. But 1 over cosine x squared can be written as secant x squared if you want, exactly. But there's also an important formula that you need to remember from elementary trigonometry. 1 over cosine of any angle to power 2 is 1 plus tangent of that angle to power 2 as well. It's very simple to prove, it's not very hard. So you might get this, or you might get it in this form. It doesn't matter, all of them are telling you the same thing. I'm not giving the answer yet, but I'm telling you that there is no difference between these three forms. These are just different forms of the same function. If one of them is given to you, the answer you already know. How do you engineer the answer? You want a function whose derivative is 1 over cosine squared. So you know that it should be tangent. The derivative of tangent is 1 over, but you have to start engineering it. But tangent x is not good enough because it will give you cosine squared x, but you want to have cosine squared kx. So you put a k here. Then there is another trouble coming in. If you do that, it will give you this one correctly, but because of the chain rule, it will be multiplied by an extra k. There is no extra k. To anticipate getting rid of that, you put 1 over k. That's it. And then plus c. Okay, but anyway, you have to know these formulas. There will be something similar to this for cosecant, which is 1 over sine x sine squared. In that case, you can write it 1 plus cotangent squared. Because I have written it here in front of you, so I don't want to spend time on them, because there are many important things coming. So these two formulas, so remember at least 1 over cosine x squared, we have a formula, 1 over sine x squared, we have a formula. But we don't have that. There is another formula, what happens if you have just 1 over cosine, and what happens 1 over sine, which I have written here as an optional. According to the reading instruction in the course, you don't need to know these formulas. Okay, so you don't need to know them. So I will skip this one and its example. But let us do one example here, example number 12. Okay, suppose that the derivative of a function f is given by this formula. I am using cotangent. Might be in the exam they will write it as 1 over tangent. If the graph of f passes through this point, find this function f. Yes? It's a very simple problem, yes? So the function, the derivative of a function is given to you in the form of tangent x plus cotangent x to the power of 2. And we know that the graph of the function, not of f prime, the graph of the original function is supposed to pass through one point. What that point is, pi over 4 and 2. And the question is that, what is f of x? Yes? So I hope that everyone agrees this is an integration problem, yes? Because f prime is given somehow with some extra piece of information, and then what you are supposed to find is f. So you want to go somehow from f prime to f. Whenever this is wanted, you just do it using integration. So this means that I will integrate so I would say that f of x is equal to the integral of tangent x plus cotangent x to power 2 dx. Okay, so here you have to be a little bit creative, because none of these formulas directly allow us to calculate this. So you have to do some calculations, prepare it for integration. So what is the preparation step here? Yes?
Right, tangent and cotangent as sine and cosine, and then we can do something with the doubling of sine.
Okay, but that would be very complicated. Yes? But if I use the formulas I just mentioned, they will be much easier. So you just raise it to power 2. So this is integral of the first one squared is tangent x squared plus this 2 times the first one times the second one plus the second one squared. Yes? And then I have dx. But can you tell me what happens here?
It's just 2.
Just 2, because tangent and cotangent are reciprocal. So if you multiply them, it becomes 1. Okay, so this becomes, if you don't mind, let me write 2 first. 2 times 1, 2. So this becomes integral of 2, and then I have a tangent x squared plus a cotangent x squared. And then I have dx. So this is why it is good to remember more or less different forms. Now, can you see that these formulas we just learned can help us to solve this problem? Yes? So for example, you see that this is one of the things that might be helpful, but the problem is that instead of 2, I need 1. But this motivates me to break this 2 to 2 ones. Lend 1 to this and 1 to that, then I use one formula here and the other formula that is on the nose. So what I can do, I can write it as integral, but this is not probably the unique way, but this is probably a good way. So 1 plus tangent x squared, and then I will have it plus 1 plus cotangent x squared, and then totally dx. Okay, so you might say that, okay, I break it right away, but breaking it right away is probably not that very good. Yes, of course you can generate formulas, I can talk about that as well. But here, I can now break the integral into 2 parts. The integral of the first 2 together, and then plus the integral of the second 2 together. And now if you are familiar, if your eyes are familiar with these patterns, you immediately catch it, yes? So can you see that? It is on the board. This one is the first one. Even it is k in this problem is just 1. So the answer to the first integral is 1 over 1 tangent of 1x. So the answer to the first one is nothing except tangent x itself. Yes? And now can you read the formula from there and tell me the answer? What is the answer to this part? Minus cotangent. Yes, very good. So it's minus cotangent x, but of course I have to put a constant c at the end. Okay, so this is your f of x. So f of x is given to be tangent. We found it, but it is not fully found because still c is missing. And this is why they have provided an extra piece of information. They are telling you that this function is supposed to pass through this point. So it means that the coordinates of the point should fit the equation of the function. So what does it mean? It means that if I replace x with this x, the output is supposed to be 2. So it means that f of pi over 4 should be 2. So this means that tangent of pi over 4, I replace every x with pi over 4, this should be equal to 2. But do you remember what is tangent of pi over 4? You have to remember these. 1. And if tangent is 1, cotangent is the reciprocal is also 1. So this is 1 and this is also 1. They are cancelled. So c is left and c is 2. And the answer that you are supposed to write at the end is what? Tangent of x minus cotangent of x plus 2. Yes? So if you want, for example, some of you might be more comfortable, I will add it. By the way, whenever you want to study notes, study the latest version, because when I go home, I will change something there as well. So if you have this one only, can you tell me what will be the answer of this one? I don't need another. I haven't written it, I will add as a remark. Okay, but if you have this one, can you tell me what's the answer? If you have 1 plus that one, you know the answer. The answer is just simply tangent with some factor. But if you don't have that extra 1, what do? You add and subtract. Very good, very good. So this becomes integral 1 plus tangent kx to power 2, but you subtract 1 to compensate for the change. But why this is good? This is valid because 1s are cancelled, so this equality is legal. But why this is useful? Because now I can break my integral to the first one minus the second one. Yes? And now I know the answer to this part. The answer is just simply 1 over k tangent kx. And I also know the answer to the second part is x. So it is minus x plus c. So sometimes you have to add and subtract because you can use the formulas properly. Understandable? Yes? Okay. Now, the next one is optional, so if you don't mind, let me just skip its formula and its example. But there are 2 more important formulas that, according to the reading instructions, we have to learn. One of them is an integral whose answer is an arcsine function, and one of them is an integral whose answer is an arctangent function. Okay? So let me describe them on the board for you. So if you have this is something you need to remember. If you have an integral whose integrand is 1 over square root of a squared minus x squared if a is positive. If you have to train your eyes to catch this pattern. 1 over the square root of the difference between 2 complete squares, a squared minus, but one of them constant. Whenever this happens, the answer is arcsine of x over a plus a constant. And then again, you shouldn't be worried about the proof because the proof is the same. How should I prove it? How? Differentiate the right hand side using the formula. And there is another one which is important to know, is 1 over x squared plus a squared without any square roots involved. This gives you, oh sorry, I forgot to write the x. So don't be lazy to write the x in the exam. So, and then this becomes 1 over a arctangent. Again, the proof is the same. You differentiate the right hand side using the formula for the derivative of arctangent, and you see that what I'm claiming is indeed true. So you have to train your eyes to catch these 2 patterns. Yes, please.
Do we have also like arc cosine?
No. Arcsine and arccosines are not independent. Because arcsine x plus arccosine x is pi over 2. So you can write this as pi over 2 minus arccosine. That's not a big deal. The same is true for arccotangent and arctangent. Okay, but let us do some exercises. I will solve one problem at least, and then instead of giving my example, let me do exam question. Okay, so I will solve this example number 14, very simple. And instead of solving my example, my example is a little bit better than the exam. Exam one is also simple. Okay. So let me ask you how we can solve this, because the formulas are in front of you. Integral I want to calculate the integral of 1 over square root of 1 minus 4x squared. Okay, we want to do this. How should I do that? You see, whenever this is given to you in the exam, I hope that you agree with me, none of the previous formulas are even close to this integrand. Yes? So, which one, so you have to know it in this way. So this formula somehow is comparable to that one if I want to compare. But it's not 100% that. So I have to fine tune it, yes? Because in my formula, the coefficient of x squared is 1, but here the coefficient is 4. So if I want to make it 1, legally it is possible. What do? You factor, no, substitution method will also work, but I haven't talked about that yet. Because we really don't need substitution method here. But how can I do that here?
2x whole squared.
What?
So 4x squared is 2x.
No, but then you have to use substitution method. Yes, I don't want to use the substitution method because I haven't talked about that yet. But factor a 4 out. Yes? So if you factor a 4 out, what happens? So this becomes the square root of 4. This becomes 1 over 4. And this becomes x squared. And this is dx. Do you agree? Of course, what you said is 100% correct. If you do it using substitution method, that's also correct. But we don't need it. If I factor a 4, I hope that you agree with me. Is that right? But now, this 4 is not a problem. Because the square root of 4 is just what? 1 over 2. So because it is in the denominator, I write 1 over 2. And then I would write 1 over, instead of 1 over 4, I write 1 over 2 to power 2 minus x squared dx. And then my pattern is complete, yes? Because 1 over 2 is not a big problem, I can pull it out. And the integral left for me is exactly according to my pattern. Do you see that? Just compare this integral with this integral. What is playing the role of a in this problem?
Half.
1/2. There is 1/2 here because of that factorization. The answer to this is arc sine of x divided by a, which in this case is what? 1 over 2. And then I have a constant c. And then of course x over 1 over 2 is just simply 2x. Okay, so let me go to the important parts. I don't think these are hard. For example, the exam question. So let me show you here. So can you tell me if we want to solve this exam question? I hope that you agree that this combination that you see here is very similar to this formula that you have here, but you have to fine tune it. So can you tell me what will be the next, the first step? Let me do it here for you. So integral, this is the exam question. Integral of 3 divided by, what is that? 2 plus 8 x squared dx. Am I right? This we want to do in the exam. So what should I do? So you have to remember this formula here. Hopefully you see that the second formula is useful. I have to be careful. Yes. So what do you think I will do now? You have to do some legal steps. You have to take some legal steps so that it becomes comparable to the second formula. So what is the... This 3 is not a big problem. What should I do with this 3? I can just take it out. So this 8 is a problem, because in my formula the coefficient of x squared is 1. But now you have experience. What do you think I will do? Take it out, yes? So this becomes 3. I factor 8 out. It becomes 1 over 4 plus x squared and then dx. So 3 over 8 is a constant, is a multiplicative constant, so I can pull it out. Then it becomes 1 over, instead of 1 over 4, I would write what?
Half squared.
Squared plus x squared and then dx. So this becomes 3 over 8, 1 over a, arctangent of x over a. Yes? But this becomes 3 quarters arctangent of 2x plus c. So you'll see the difference. In arcsine, we don't have the factor of 1 over a. In arctangent 1, we have a factor of 1 over a as well. Why is that? You just differentiate, you see that you really need that factor in the second formula. Any questions? Okay. Let me, if I have time, I come back to example 15. But let me teach you these two. In Sweden, we usually do not study these. If you take mathematics 5, some teachers will teach them. But usually we don't have these in the high school. So all of these, except these are, by the way, arctangent, you are right. These are also not in the high school. But anyway, we want to now develop techniques of integration. There are 3 ones that you need to learn. One of them is U substitution. Probably from my perspective, this is the most important one. Okay? And the second one is integration by parts. Hopefully I can cover at least some examples of these two. And the next one is the method of partial fractions that we will learn next time. Okay, so what is the method of U substitution? So U substitution method is also not hard. So do you remember what type of formula is this? Do you remember something about this combination f prime of g of x times g of, yeah, that is the chain rule. Yes, so if you see this, of course you can immediately guess that one, because if you see integral of f prime, if I have 2 functions involved, f prime after g of x multiplied by g prime of x dx, I hope that you can let me write the proof here. So what the answer is, here, what can you write? You can write it as f of g of x totally prime, as we learned in the chain rule. If you open it up, this becomes this. I copy and paste the integral sign. I just copy and paste dx. But now integral of a derivative is just this function, but probably plus a constant. So the formula is, of course, the reverse of the chain rule, so that is not something strange. But mastering this technique is probably the most important one. And you will start learning it, so you have to train your eyes to catch the patterns if the problem is complicated. For the simple ones, it is very simple. For example, and by the way we write it is that, if you don't mind, let me replace g of x with u, so that is a better way to remember it. So f prime of u, this becomes u prime, and then dx is equal to, the answer is f of u plus a c. Okay, for example, let me just give one example here. If I give you this 2x, and then I have x squared plus 1 to power 100, and then I have dx. Okay. If this exponent is small, you don't have any problems. So if it is 2, you don't even need to know this method. You can solve it. How? By raising it to power 2 and multiplying and open it up. But for the 100, in principle it works, but it is impossible practically. My advice to you is that I want to teach you in a practical way. If you want to calculate this, train your eye to see that, is there any part in the integrand so its derivative up to a scaling factor is also appears as a factor itself. Okay, let me repeat. For example, here, it is not hard to see that if this one I consider, what is its derivative? Its derivative is 2x, and you see 2x as a factor. What do I mean by factor? It is multiplied. So whenever you see this is happening, it's already a good indication that the most important technique to solve this is method of substitution, as I want to describe here. Whenever this happens, take that expression to be your u. Okay? And then start differentiating the left and right. But in this technique, of course, I can write u prime is 2x. If you want, we can write it. So what is u prime? Is 2x. And then let us write it back here. So what happens? It becomes u to power 100, and then you have u prime dx. Okay, so if u was x, so if you could already solve this one, yes? What is the answer to this one? 1 over 101, x to power 101. Okay, this is also the same thing because you have your u prime next to it. It is a chain rule. So it becomes 1 over 101, u to power 101. As soon as if you don't have that u prime, it is not possible. But if you have that u prime, it's the chain rule. Because if I ask you to differentiate this, what do? You pretend that u is x, you differentiate, you get this term, but you also multiply by u prime, which you have it. Is that right? Okay, so this is plus c. But you shouldn't stop there, because the integral was expressed in terms of x. This is the variable you brought in to solve your problem, then you have to switch back to the original one. So this means that you continue one more step, and then instead of u, you put x squared plus 1 to the power of 101 plus a constant c. Is the method clear? So the idea is that an integral is given, might be the integral looks complicated. For the first steps, try to think, is there something there so that if I take it u prime appears there up to a scaling factor as a multiplicative expression. What do I mean? I take this one u, its derivative is 2x, and 2x exactly appears as a multiplicative factor. This is already an indication that this is a good method to solve that problem. Take this one u, the rest you can do, because I saw a lot of questions in workshop problems, they are proposing you what is u substitution. If that is proposed, there is no difficulty, because everything after that is algorithmic. You differentiate, but I don't want to do it like this. I will try to do it exactly written in your book. If I want to solve this problem, I write like this. If I want to solve that, I realize that I take u to be x squared plus 1. I differentiate both sides. I find the differentials. The differential of the left with respect differential of a function means derivative of that function, but multiplied by the differential of x. This is the way we write, and this is written in your book, okay? So what I would do, I would write it as du. Du is the derivative of this function, which is 2x, and times dx. Okay? So in this way, what happens, instead of this together with that, I can write du. So then my integral, if I call it I, becomes equal to this one together with that one is called du. So I will write it. And then this one, I myself called it u. And then I have integral. Okay, but be careful here now. In this form of writing, which I don't prefer, it is unnecessarily complicated. You have a u variable and you have an x variable. If this variable is still x, you should have this u prime there. But in this way, which is a better way of writing, what is the variable of integration here? U. So you just do it exactly as if it is x. And if you don't mind, I will continue in this way, which is also written in your book. And then, of course, I have to switch back. Okay? It needs a lot of practice. Let me solve more problems for you. So there are a lot of questions here. I don't know where start. Which one is probably a good starting point? Okay, let us first solve the number 1. Can you propose to me something about part 1? Yes. So here there are a lot of exercises here. Please try to do all of them at home and especially exam questions. There are many of these questions there. But let me pick some for you. For example, let us start with this simple one, number 1. And